Okay, Professor, now the
Okay,
comment.
thank you very much. And yesterday we talked about ignition. So in terms of ignition chemistry, ignition theory, and then how plasma can enhance ignition. What we conclude that plasma can significantly enhance ignition due to that the new chemistry by plasma and the new radical production and probably chamber entry reactions as well. And today we try to talk about the flames. The question to ask is really, can plasma enhance flame speed? And yesterday you heard that a lot of experiments basically showing that, okay, plasma can stabilize flames, can enhance a flammability limit, can increase flame speed. The question is that is it real? If it is real, then how? Um, so let's look at that first by looking at the experiment, right? In combustion, everybody know that there is a S curve that's showing that flame temperature or flame speed as a function of, for example, flame residence time. You have a long residence time and ignition happening, and a shorter residence time, extinction will happen. And the fundamental question is that how does plasma change this curve? So this is the foundation of combustion. If plasma can change this curve, that means plasma is very effective. If it's not, then probably not much. So this is an experiment done by the Wenting when he was at Princeton. We yesterday we introduced already that we're showing that the OH a number density as a function of fuel mole fraction. As you can increase the fuel concentration, that means that you increase fuel reactivity. That ignition will happen and become a flame, and you reduce fuel concentration, and that the extinction will happen. So this is a typical S curve, just like showing here. So by using plasma at a oxygen concentration at 62%, for example, in methane, so you can see that the ignition point is dramatically shortened and to a low concentration. And then even extinction limit is extended. From this figure, and what we can conclude is that we conclude that plasma, at least they can accelerate ignition to make that the ignition time is so short that if you put a fuel and then there's some reaction will be there. And in addition, this curve also shows that even though that the plasma effect on flame extinction is smaller compared to ignition, but it still can extend that the extinction limit a little bit. And then the question is why? Can we do an experiment, can understand whether this is just a thermal effect or whether it's a chemistry effect? And then in terms of a cool flame, for example, if we replace the fuel from methane to dimethyl ether, is DME, and we can see that this is at the lower fuel concentration, and you can see a lot of formaldehyde is formed. A formaldehyde formation is a clear indication about low temperature chemistry, LTC, of dimethyl ether. So you can see that when suddenly when you further increase fuel concentration, and suddenly this formaldehyde disappears, and then going to a hot ignition, you have a high temperature flames. So what this figure says that it says that plasma can enhance a low temperature flames or low temperature combustion, and then trigger that the transition from low temperature combustion to a high temperature combustion. So this is very interesting and showing that if you can control low temperature combustion by plasma, you probably can accelerate that the combustion as well. So this is indeed that, for example, at the 672 tau, with the increased plasma frequency and oxygen concentration, you can see that plasma can enhance low temperature chemistry at a very low fuel concentration. And then the low temperature combustion transition to hot combustion is smoothly transferred. That means that you are accelerating the flame from a cool flame to a high temperature flame very smoothly without a reignition process. So again, this clearly shows that plasma play a big deal in terms of low temperature flames. Why is that? Um, so to understand this question, and we try to say that they look at the chemistry. And the chemistry says that at high temperature, which is at above, let's say 1100 Kelvin or 1050, that the fuel molecules is attacked by OH radicals and then they form a free radical. That high temperature free radical is not stable and they either break down to a vinyl radical or oxidized by the OH radicals and form a formaldehyde. And these things continue to be oxidized to form a HCl, and this HCl will couple with H plus O2 reaction that form a lot of OH, and that reaction with HCl and form a CO and CO2. This is a high temperature chemistry. So if plasma can compete with a high temperature chemistry, you have to compete with H plus O2 chemistry. The question is, can plasma do that? It certainly can do for ignition, because ignition, you don't have radicals. But for flames, you have a lot of radicals. Can plasma win? So that's the question. At the intermediate temperature, so let's say that below 1050, so the free radicals is not able to be dissociated into a vinyl radical. They have to react with RO2 and or HO2 and to form some hydrogen peroxide. This hydrogen peroxide is quite stable until 1150. So they decompose to two OH radicals at the temperature close to 1050 Kelvin. And this process is quite slow, so that plasma may create a lot of HO2 and OH accelerate this process. At a low temperature, you can see that this, everybody knows that the few radicals, it cannot directly react with HO2, and they basically attach to oxygen and form this alkyl peroxy radical. And this thing, isomerization becomes QOH. And then add another oxygen that form this O2QOH, and then go to isomerization and decompose to keto peroxide and form a multiple OH radicals. So this is a fast, slower. So what is the role of plasma? The plasma generates this electronic excited oxygen, O radicals, ozone, and molecular oxygen excitation and the vibrational excitation. And then these were going to be dramatically accelerated the low temperature chemistry the most, and then more and the least in terms of from chemistry point of view. But however, this combustion chemistry is almost well developed. And you say probably, let's say, talk about flame speed, ignition delay, you're talking about 20 to 30%. That's not a big deal in terms of plasma. In plasma, there are so many reactions. We don't know even in orders of magnitude in terms of reaction rate. For example, this type of reaction rates, and we don't know how fast that reaction rate will be. And all these reactions are very low temperature. It's very difficult to be predicted actually using quantum chemical computation. And then, so therefore, if you plot, everybody is familiar in terms of ignition. If you're looking at the ignition curve of enhancement, they have two-stage ignition, a low temperature ignition, they have a high temperature ignition. So low temperature ignition will almost happen between 600 to 900 Kelvin, and high temperature ignition happen probably 1100 Kelvin. If you're looking at whether plasma can do anything to help this enhancement combustion, if you have to look at the reaction process. At high temperature, you can see above 1100 Kelvin, and the plasma generates some radicals, but the flames can generate radicals by this H plus O2 chain branching reactions. These reactions is very fast, and if your temperature is above 1200 Kelvin, for most of the high temperature flames, the temperature are indeed much higher than 1200 Kelvin. So therefore, this radical production from this chain branching reactions is much, much faster than the plasma generated radicals. So therefore, for high temperature flames, in principle, plasma has no effect in terms of enhanced flame speed other than raise the temperature. So therefore, for flames, the plasma probably is only raise that the temperature to enhance flame speed, not even no chemistry effect. But for intermediate temperature, you can see that you have a fuel oxidized into formaldehyde. They react with a radical, form HCl. This reaction, particularly when X is OH, this is a dominant reaction of intermediate time step. They generate heat Also, they generate HCO, which promote that the formation of HO2, hydrogen peroxide, and OH. This reaction is quite slow compared to this one. So that plasma can enhance this reaction. At the low temperature, as I said, this alkyl peroxy process is very, very slow. So plasma can dramatically enhance that low temperature fuel oxidation. So what kind of experiment we want to do? And when I look at this figure, and I created in 2014, I told that the people in my lab said, go ahead to do plasma assisted low temperature combustion, because this is going to be a big deal. You'll see something interesting. And so if you do a simple numerical simulation and about ignition delay as a function of temperature. So this is a high temperature ignition, this is a low temperature ignition. If you, let's say plasma can give you 100 ppm of radicals, OH, you can see at high temperature, it does not really change much. But at a low temperature, it does change a lot. But at the intermediate temperature, you can see that the solid lines and you can low temperature combustion. The low temperature ignition is going to be dramatically accelerated by this OH production. So what does it mean? It means that I try to review again at high temperature above 1200 Kelvin or 1100 Kelvin. The chain branching reaction is governed by this reaction. A plasma may not do anything to help it because it cannot compete to win this, because this guy is very fast and when the temperature is above 1200 Kelvin. However, for intermediate temperature, these are the two chain branching reactions. The plasma can win. I will show you later. For low temperature, the chain branching reaction is governed by these process. This is much, much slower at 600 Kelvin. The plasma can do a big deal to accelerate this reaction process. So what kind of research you want to do? Certainly, you want to see plasma effect. You want to see how does plasma promote intermediate temperature flames, cool flames, and low temperature fuel oxidation. So that's something that we did in the experiment we showed you yesterday. That so after we draw that kind of figure, and in 2014, we said let's do a plasma to see whether we can see a cool flame in the laboratory. So you can see by putting a plasma there, you can see a high temperature flames on heptane at a very, very low pressure, 60 torr. Normally you don't have cool flames, but with plasma you can see a very, very bluish cool flames. And even with ozone addition, you can see that even you can see a cool flames and a hot flame at the same condition, same experimental condition. So this means dramatically prove that theory hypothesis that plasma can dramatically enhance low temperature combustion and intermediate temperature combustion. Experimentally shown. So with that, we just showed you yesterday. Now, with that help of plasma, you can see that from mankind understand that we know the hot flame. When the God come to the earth, they say, okay, how many flames we create? And artists plot that, okay, there are three different colors, the red and the yellowish, and then the white yellow. We didn't understand what does it mean, but today we understand that with the recent study and using this plasma-assisted sensitization of fuel, we observe there are three different kinds of flames. For diffusion flame, for example, you have hot flames, is above that maybe 1300 Kelvin. You have a warm flame that you have two different flame structures, and that is between probably 900 to 1100 Kelvin. And you have cool flames that is below probably 800 Kelvin and above 600 Kelvin. So you have cool flames, you have warm flame, you have hot flame, just like the artist plotted before. All this thing observation is just because we used plasma or ozone to sensitize the fuel and then enabling us to observe it. So plasma does play a good contribution to promote that the fuel reactivity. So then what? So then what is the chemistry? And we're talking about. So we collaborate with Niels Hansen at the Sandia. Let's say that what is the chemistry in terms of ozone reaction with a ethylene. So when you have ozone with ethylene, the ozone will directly insert into this ethylene CC bond. And you can see form this kind of a primary ozonide. This primary ozonide, it can be formed in room temperature. And then they you break down into a Krigi intermediate, CH2OO. This Krigi intermediate is very reactive. It can decompose and into HCO and OH, and or they can generate into decompose to a dioxyran and then form a H radicals and water and CO2 to give you heat. So, and with that kind of low temperature combustion promoted by ozone, then we studied that how does ozone enhance that, for example, biodiesel methyl hexanoate. So if you see this figure, you can see from low temperature, 300 Kelvin to 800 Kelvin. Without ozone, you can see this green line and this dashed line. You only can see that the low temperature oxidation started at 550 Kelvin. But with that the ozone addition, and you can see that there has a region that they have extreme low temperature combustion, that even above 450 Kelvin, and there is a oxidation window there. This is all because ozone decompose to form atomic oxygen around 430 or 420 in a flow reactor that promote low temperature chemistry to be seen. Again, this experiment is showing that plasma can significantly enhance that the low temperature chemistry and at very low temperature, even at 450 Kelvin. So now what is the plasma can also generate NOx. When you have plasma in the air, then generate NOx. How does NOx affect that the oxidation? So this is a recent figure and down in collaboration between Nancy and Princeton. You can see that with N-pentane, they have a low temperature chemistry. Without a NOx, NO, you can see that fuel oxide around 550. And then you have a low temperature reaction window and then NTC region. But if with a NO addition, you can see the low temperature chemistry now is delayed dramatically. But the NTC effect in the intermediate temperature is suppressed. In other words, they accelerate a reaction at the intermediate temperature, but they delay the reaction in terms of a low temperature chemistry. The reason is because low temperature chemistry, they require this alkyl peroxy radicals. But once you plasma generate NO, they're going to convert this RO2 into RO becomes NO2, suppressing that the alkyl peroxy radicals and slow down the low temperature chemistry. However, at intermediate temperature, you can see the NO react with HO2, they form OH. They convert this low reactivity HO2 into high reactivity OH. They promote reaction at the intermediate temperature. So this is very interesting when you're looking at the flames. And then Manley did the experiment. You can see that the flame temperature as a function of strain rate in a countable flame. You can see there's three different kinds of flames: the hot flames, the warm flames, and cool flames. You can see by adding NO, the intermediate temperature flames, you can see that they are extended to a higher strain rate. That means the reactivity is increased at the intermediate temperature. But for cool flames, you can see that the reactivity is dropped, and the NO really slightly suppressing that the cool flames, but promote warm flames and hot flame both. So therefore, plasma can generate ozone and NO, and these things are very stable and a long time. They can dramatically kinetically change your combustion chemistry. And at Penn State, and Professor Rich Yetter and develop a flow reactor. You can see from here by a dielectric barrier discharge, DVD, and he measured that N-alkanes, different N-alkanes, as a function of temperature. So this is without plasma, and this is a with plasma. You can see that this, plasma activation dramatically shifted that the curve into low temperature. So once again, that experiment show plasma can activate low temperature combustion extremely well. So now the question is that, okay, plasma can do a lot of things, can accelerate low temperature combustion, intermediate temperature combustion, but may not affect that the high temperature combustion, because that the plasma chemistry is not fast enough compared to that chain branching reaction by the flame itself. So you look at the flame theory, you probably take the class from Professor Paul Clavine, but I don't want to get too much detail. You just say that you have a flame front and from a upstream to the burn state. If you write down the conservation equation and temperature and the fuel, and then if you add these two equations together, they cancel this reaction, and you get that the adiabatic flame temperature is a function about fuel concentration and heat release. If you integrate this equation by adding them together from that, just right before the flame front and after flame front, you are integrating this from the flame to right away after flame front, and you get this kind of a reaction diffusion zone relationship between the temperature and the fuel mass fraction. So now that you have to do an integration about in the reaction zone. In the reaction zone, that the reaction is governed by diffusion and reaction. So you can integrate this reaction equation from that the unburned to the burned. And using that relation we derived before, you end up with this kind of jump condition that the fuel gradient before and after the flame. After the flame is zero, and before the flame is proportional to the reaction rate like this. If you substitute this with the previous reaction diffusion zone equation, what do you get? You get that this is that flame speed. You get the flame speed is like this. So this is in the Professor Law's textbook. Everybody, I just want to give you some kind of derivation. It says that flame speed is function about that the activation energy and reaction rate and everything. And the question is that can plasma change the activation energy? So the argument I brought you to before is that plasma can't, because for flame, that the activation energy is governed by H plus O2 reactions. And that at high temperature, plasma cannot win. So therefore, plasma has a little effect in terms of flame speed. That's my judgment. And then the question, what if you have heat loss? Okay, if you have heat losses, you can add some kind of heat loss into that equation. You can do the same asymptotic analysis. I don't want to go to the detail. You can follow my slides or follow Professor Paul Clavine's slides. And you can get that the flame speed is like this. Okay, so this is the flame speed. The normalized flame speed to the adiabatic flame speed and is proportional to 2H. H here is indicated by the heat loss. This TAD square to fourth power is the heat loss. We plot that the M is that the ratio of flame speed to the adiabatic flame speed to the heat loss. You can see that flame speed decrease as the heat loss is increasing. And at a certain point, that the flames will be extinguishing if that the H becomes to E to the power of -1, and the flame speed drop to E to the half power, and then this is the extinction limit. So therefore, that the heat loss can quench the flame. But even though plasma cannot do anything to help that the chain branching reactions, but if plasma can give you heating, so you can make that the extend the flammable limit because of plasma heating. This from theory point of view. And this is also quenching diameter. If you know that the flame speed is defined by this, if you in a channel that the heat losses is proportional to the Nussel number, so you can rewrite that equation, make the flame speed is a function about my Nussel number. The Nussel number is that the heat losses. If this one is become to the inverse of E, and then you have a quenching diameter, that quenching diameter is like this. It's proportional to your a zero deficit number beta, and you have proportional to your Nussel number and flame thickness. So therefore, the quenching diameter is proportional to your function of flame thickness and then Nussel number. Again, that this is a computation by Professor Matlon, I think, that they compare the theory with a computation. So then how does plasma do that? Well, plasma cannot do the flame again, but the plasma can get heating into the system, can suppress that the quenching limit if you have a plasma, because plasma can penetrate at the length scale of the band length is much, much smaller than the quantum diameter of a flame. So now I try to give you review something maybe Professor Clavine or combustion textbook does not give you. So most of the flame speed is not only a function of the reaction, but also is a function of the Lewis number. Most of the symptotic analysis and give you theory saying the Lewis number is something smaller, very close to unity. So what if the Lewis number is not unity, close to unity, is big or is very small? And how does that affect your burning limits of a flame? All right. So you can write down the governing equation. Let's say this is a countable flame, and you have strain rate, which is A, and you can write down the governing equation about convection, diffusion, reaction rate, and then you have a heat losses somewhere. So then the question to ask is here, how does the flame speed or depend on the fuel concentration, right, or strain rate? So you can do the analysis. I'm not going to do too much detail. You can follow my slides, and you can do, for example, normalize the two equations, and then you do the perturbation about temperature, this number, for example, and then you do an integrator of the convection diffusion zone with no reaction, and you develop this jump condition across the flame front from a unburned region to a burned region, and then you do a matching jump condition about the mass and energy equation. So with that, you put it back to the governing equation, you can get the solution. So this is the perturbed reaction. This is the convection, diffusion, and correction of Lewis number from here, and this is the heat losses. If you do that, and you can get that, okay, this is the solution. The solution is that the strain rate A is a function of my flame location. Remember, the flame location times indicating the flame speed. So this is that flame speed, and this is the strain rate. The G1 is a parameter. I show you what is G1 here, and it's proportional to that PF. PF is the perturbation of flame temperature by half. Okay, how does the flame is perturbed in a straight flames? First of all, the flame temperature is going to be affected by your Lewis number, L, right? The L is the Lewis number. And then it's affected by the heat losses after the flame due to radiation, and also affected by heat losses in front of the flame due to radiation or something else. And these functions of G1, G2 is defined by this way. And then you can put into a MATLAB, you can compute this as a function of flame speed. If you think that, okay, my flame is far away from my stagnation plane, so in that case, this one becomes the unity, and the flame become a planar flame, and this equation here, it becomes like this. The flame speed m is defined by the flame location with square root of strain rate. It's reduced to the previous equations. So therefore, this theory provides a connection between a planar flame propagation and the strength flame speed. It's very interesting if I show you that. So let's say that I have a mixture with Lewis number is less than 1. So you can see that this is the flame location and this is the strain rate. So as you increase the strain rate, you can see, and the flame temperature decrease, and extinguish. This is a stretch extinction. As you reduce the strain rate, it's also extinguished. That's because when the strain rate is very slow and the radiation heat losses becomes large, and the flame is killed by radiation. So you have radiation extinction here, you have straight extinction here. The flame can only survive in between when the fuel mole fraction is lower. If you increase the fuel mole fraction, then it's interesting. You can see that you have this kind of a stretch extinction, radiation extinction. There's a flame isola, and at a very low strain rate, you have another region that a flame can be survivable. As you increase the fuel concentration is slightly, you can see that there still has a flammable region at the higher strain rate, but there is a flammable region at connecting to the zero strain rate. So therefore, at even as strain rate is equal to zero, the flame is still exists. So this is defined that the flammable limit of a planar flame. If you further increase the fuel concentration, you can see that this far field flame connecting to that the high stretched flame, they become one isola. This is very confusing to you, and you don't understand this. But but it's very simple to understand that the extinction limit. So many of you did countable flame. This is the experiment done by Professor Maruta when I was in Japan. You can see this countable flame. You can measure that extinction strain rate as a function of equivalence ratio for methane. And for methane, you can see that, okay, if you reduce that equivalence ratio, extinction limit getting lower and lower, at a certain point, and the flame does not exist. But there is another, at the same equivalence ratio, you have two extinction limits. One is at high velocity, the other one is lower velocity. These two limits is exactly that predicted by here. Stretch at high strain rate, radiation at the low strain rate. So this curve basically defines that the burning limit, a flame can only exist between. So this point is that they call flammable limit. But this flammable limit is very much lower than the flammable limit of a planar flame of methane. So people did not understand why that the stretched flames of methane has the lower burning limit than the planar flame, and why. But if you do the same experiment for propane, you can see that the extinction limit monotonically decrease. And they linearly extrapolate to that the flammable limit of a planar flame. So why does a propane air mixture, a stretched flame, can be linearly extrapolated to that the burning limit of planar flame? Why that the methane is not? This is the question. So I was very curious to do that, and later I plot that the figure. A figure basically summarizing that the computational result. For if you have a mixture with a Lewis number, let's say 1.4 with this kind of helium dilution, at a very low concentration, you can, let's say equivalence ratio, you have a flame island, which is confined by at a lower strain rate and a higher strain rate. As you increase the equivalence ratio, and then this flammable region is increasing. At the same time, you have a far field flame that can only exist above the flammable limit. And when this two flame, for example, at equivalence ratio of 0.469, these two far field flames and this near field flames, they combine together, they form this kind of a flammable curve. So therefore, you have two different kind of flames when Lewis number is less than 0.4. One is near field flames at a high strain rate. The other one is a far field straight flame at a lower strain rate. They define different burning limit. The far field flame burning limit is like this, the dashed line, and then the near field flame is governed by this limit and the radiation limit. So if you plot them on a curve, you can see this is the equivalence ratio. This is the strain rate. You can see that this is clearly that you can see when you reduce your equivalence ratio, you can see the strain rate decrease. This is extinction point. And this is a radiation extinction. This is a straight extinction. And there's a far field flame. This is a near field flame, which is like this line. There's a far field flame, which is extinction limit is governed by this line. You can see this is why for methane, for Lewis number less than 1.4, you cannot extrapolate this to obtain the flammable limit for planar flame. So this is, if you plot that curve here, you can see this is the experiment, this is the computation. You can see that for Lewis number less than 1.4, and then you cannot extrapolate this to obtain your flammable limits. You can only using the far field flame to extrapolate this. And same for hydrogen. And you can see I call this a G curve, and they define the relationship between a stretched flame burning limit and then a planar flame burning limit. They cannot be linearly extrapolated. And for Lewis number larger than 1.4, larger than a critical Lewis number, you can see you really can extrapolate. This is a planar flame. This is at the this is a far field flame. This is a near field flame. They are the same thing. So this explains why that the burning limit for mixtures with different Lewis number higher than the critical Lewis number and lower than the critical Lewis number, they have a different kind of flammability limits. So this is the same thing I want to share with you, because that the most of the combustion book did not discuss it, and I think that you should understand it. So then the question that how does plasma can enhance this flame speed and or not burning limit? So we did this plasma enhanced flame speed. So using a countable flame, again, we're using hydrogen, we're using a gliding arc, and try to see whether that gliding arc can activate that the oxygen can enhance my extinction limits. Here's the data you can see from here, that extinction strain rate is increasing with that the methane concentration, of course, without plasma. With plasma, extinction limit is increasing with the increase of plasma power. Well, that's exciting. So this result, I got Air Force funding because, but if you, the result is really disappointing when you measure that OH concentration by comparing that the plasma activation towards that heating only. So if you do a heating to the same flame temperature with this plasma power, the OH concentration is the same. What does it mean? It means that plasma has no impact to my OH concentration if that the flame temperature is the same by plasma heating or by electrical heating, raises the flame temperature. All right, so the plasma only play a thermal effect to enhance the flame stabilization. This is exactly what I said before, because H plus O2 reaction is so fast as the flames. But plasma can generate a lot of other things that flame doesn't. For example, as I said, you have NOx, you have ozone, you have O2 singlet, you have radicals, you have all other excited species. And the question is, what are the effects of these species in terms of flame propagation, particularly for O2 oxygen singlet delta? And long lifetime species and short. So we try to understand what is the ozone effect of flame speed for methane and propane. We did some experiment. We see, okay, by increasing ozone, the flame speed is increased very, very little, and a few percent. So this few percent mostly are by thermal effect, okay? Enhance that the thermal effect. And we said with that O2 singlet, because in combustion, as I said, H plus O2 reactions generate OH plus O. This is a dominant chain branch reaction. But if plasma can generate O2 A singlet, it's excited states of plasma, this have 1 electron volt. This reaction is, in theory, is 100 times faster than this. If we can generate 1% of these guys in a oxygen, we can, compete with that the H plus O2 chemistry. The question is that, can this reaction enhance flame speed? So we did this experiment and try to measure O2 singlet and to see how O2 singlet will be enhanced flame speed. And we did this kind of lifted flame, and you have a flame lifted here, and we're using a plasma to generate. This is a microwave, and this microwave is going to generate a O2 singlet. This O2 singlet is measured by ICOS cavity. It's just like a cavity Radan spectroscopy. And we measure ozone, we measure NOx at the same time, and try to understand how that the plasma generated a long lifetime species can affect the flame speed. We'll talk about a diagnostic later, but I just want to show you the result. The result, you can see that, okay, by increasing that by measuring that the O2 singlet, generation, we produce 5,000 ppm of O2 singlet. That's a lot. And we see that the flame speed is only increased by a few percent. That's really disappointing. We thought that this reaction is so fast, it's going to dramatically enhance double my flame speed. But in the end, in the result, we only have 2 to 3% of flame speed. Why? This is because at that elevated temperature, this O2 singlet, they are not stable. They will be quenched. So therefore, just using that the kinetic rate constant to estimate flame speed is misleading. Again, it says that the plasma does have a little effect on terms of flame speed because it doesn't change the chain branching reaction rate. And then we try to measure how much that the atomic oxygen production in that in a plasma, and you can see that this is that basically using TALIF, 2-photon laser induced fluorescence, and try to show you can indeed with increased plasma frequency you have increasing atomic oxygen generation that enhance the flame speed, enhance that the strain rate, but this strain rate is mostly that it's still by thermal because the O production is very, very small. You look at this number, that the atomic oxygen production is very, very small compared to flames. As I said yesterday, that in Professor Wenting Song's experiment, and he showed that ozone reaction with ethylene did increase that flame speed. And by increasing the ozone, you can see the flame speed is increasing, the flame city down. And why do you say that the flame cannot change the flame speed? Why does Professor Wenting Song experiment show that the flame speed is increasing? Is because the different story. It's because the different story is like this, as I said yesterday, that when you have ethylene, the ozone reaction with ethylene promote low temperature chemistry. If you have low temperature chemistry here, you can see that the fuel is already partially oxidized in front of the hot flame. So you are changing the chain branching reactions so that the flame speed will change. So let me repeat again. Plasma cannot, enhance flame speed if that the dominant reaction is still H plus O2 reaction. But plasma can change flame speed if you create a new chain branching reaction, such like this. Okay, ethylene reaction with ozone, that is ozone lysis reaction. That's a new reaction pathway that can enhance flame speed. All right. So this reaction, if you look at the picture, it looks like a pre-ignition. It's some kind of low temperature ignition, pre-oxidized mixture, and so that the flame speed can increase. In combustion theory, most of the people develop that the flame speed is only a function of flame temperature. They have nothing to do with ignition. But if you look at this picture, that the flames downstream is already affected by ignition upstream. The question then becomes, how does that ignition affect the flame speed? What if that the ignition Dunker number is high? For example, in a RCCI engines, you have flames. For example, in a cavity stabilized flame, your mixture has a very high temperature, a lot of radicals. The ignition time is very short. What is the function between flame speed is a function of ignition Dunker number. Most of the flame speed given you in combustion book is that the ignition Dunker number is 0. Therefore, flame speed is the only function of my fuel or my initial temperature, has nothing to do with the ignition. But if that the flame timescale normalized by ignition delay time, which is very short in this kind of geometry, and if this one is close to unity or is larger than 0, what happens? So if you're looking at this, you can do a very simple, you can look at the paper last year. You can see that, okay, so the flame structure now is, in addition to the reaction diffusion, reaction division zone, you have ignition zone. So you have additional reaction zone that makes the mixture is partially oxidized due to ignition. And then this partially mixed a reactive fluid going to reaction diffusion zone for the flame. So therefore, you analyzing this flame structure, you are obtaining an equation of flame speed. Now is a function about your flame speed of when the Duncker number equals 0, multiplied by this parameter. This parameter means that the flame temperature minus that the ambient temperature, the autoignition temperature minus that the preheating temperature by autoignition. If that the ignition, if TP, the pre-ignition, is equal to autoignition, that means flame speed can be infinity. For ignition-assisted flame, flame speed can be infinity if that the pre-ignition is strong. So how to estimate this the TP? That this the temperature of pre-ignition of is governed by your ignition Duncker number. So if you will plot the flame speed, normalized flame speed as a function of Duncker number, the theory basically gives you that the flame speed is exponentially increasing with the ignition Duncker number. Then you said, oh, Professor Ju said, plasma does not enhance much about the flame itself, but plasma can accelerate ignition. Well, what if plasma can accelerate ignition, make this ignition time is even shorter than the flame time? What happens? It will become ignition-assisted flame. In that conditions, plasma can dramatically enhance that the flame speed when that the flame is ignition-assisted flames. That is happening in this kind of a stabilized region. All right. So that explains why people observe that the burning limit is enhanced, the flame speed is enhanced, because of that is due to that the plasma enhanced ignition-assisted flame propagation. All right. So let's look at another phenomenon. Yesterday we showed that in a small engines that and if you without plasma, you are the engine does not work, and even at the near stoichiometric conditions. And with plasma, they can work at very lean conditions. This is very puzzling, is because that if your mixture is near stoichiometric, why cannot your engines cannot be stable? So this means that ignition is failed, even at stoichiometric conditions. And why would that the plasma can enhance it? So this is a very puzzling question. So if you're looking at a relied afterburner, so if you're looking at the flight speed, when you go to flight speed and then your altitude goes to higher, the pressure will be lower. So therefore the flow speed will be higher too, and so the flame speed actually that the decrease, you depend on the N reaction order, the flame speed actually increasing with the decrease of pressure. So, but at high altitude, you have an issue to stabilize the flame. But at high altitude, your pressure is lower, your flame speed should be higher. Why that the flame stabilization is a problem at a high altitude? Because the flame speed is high. You should imagine that the flame stabilization will become a problem at higher pressure because that the flame speed is lower. But this is what is the problem? So the problem that is that ignition energy. So if you have a mixture in the engine, even if it's stoichiometric, if the pressure is lower, you may not be able to ignite it. The question is why, all right? So what governs that ignition success or failure? Is it governed by energy or is it governed by something else? So let's look at that. You have a Lewis number, which is that defined by the thermal diffusivity with mass diffusivity. For jet fuel, normally that the Lewis number is larger than 1 because the jet fuel molecule is very heavier. So what is governing the minimum ignition energy? If you're looking at the paper by Lewis and Van Ebel, they said that the minimum ignition energy is defined by a flame thickness, that you have to raise the temperature to adiabatic flame temperature and multiply by volume of flame thickness. This energy becomes ignition energy. If this is true, you're using that laminar flame speed theory, it says that the ignition energy will be inverse function of Lewis number. That means the larger the Lewis number, the lower the ignition energy. But that's not true. That's opposite to the experiment. And then if you're looking at the theory from Zeldovic's book, it defines that the minimum ignition energy is defined by a flame ball, which is that ignition energy is a function of the flame ball size multiply this temperature. And you have to ignite the mixture to a flame ball size, which means that the ignition energy is a function of Lewis number. So if you look at these two theories, they are opposite. And which one is right? Which one is wrong, right? So if you do a very Professor Chen, and right now he's in Beijing University, he worked with me. I developed this kind of theory, and and he said that okay, my flame temperature and my heat addition in terms of energy as a function of Lewis number and flame speed is governed by this equation. All right. So if that is the case, what is the governing parameters for ignition? If you're looking at the picture, basically saying, okay, the flame speed, normalized flame speed as a flame radius. If the flame radius is infinity, of course, that the normalized flame speed is equal to adiabatic flame speed equal to 1. But if the ignition energy is lower, and then you have ignition, the flame speed will decrease as the flame grows, and eventually will quench until at a certain energy, which ignition energy is high enough, that the flame speed decrease at a certain point, they reach to a minimum flame speed. And after that, they automatically increase and then reach into adiabatic flame speed. So therefore, the minimum ignition energy, it is that energy you can drive that flame of a stretched flame connecting to the far field flame. So you have a minimum transition point, define that the critical radius. So this size of the minimum velocity define that the critical radius, the ignition energy has to drive that flame to reach to that critical radius so that the flame can propagate by itself. Otherwise, ignition will fail. So ignition energy is actually governed by a critical radius and not by that the flame thickness. So if you do experiment, some of you did experiment in Frigo flame, you can see that the flame speed is decreasing. You can see the flame speed is as function of time, is it decreasing, and then propagated by itself. This size determines that the ignition energy. And if you don't believe me, and we can calculate that what is that minimum ignition energy by using that the cubic of that the critical radius. You can compute for different Zeldovich number, activation energy for different Lewis number. This is Professor Chen calculated this, and you can see that they plot a linear line for no matter what is your Zeldovich number, no matter what is the Lewis number, ignition energy is dependent on the critical radius for all different kind of Lewis numbers and activation energy. So therefore, in order to make a successful ignition, it's very important to drive that ignition kernel larger than this critical radius. This critical radius is defined by the chemistry and pressure. But lower pressure, critical radius is bigger. That's why at high altitude, you have a larger critical radius and your ignition is become difficult. So if you measure that the critical radius in the laboratory, which we did for jet fuel, you can see as you go to linear, your critical radius is increasing. As you go to lower pressure, your critical radius is also increasing. So that's explain why at the low pressure fueling condition, ignition in engine is become difficult because of this critical radius. All right, so I try to save time. And so in order to overcome the critical radius, and we can show you that if you put all the energy into a single spark, or you split the energy into 3 sparks, make the 3 sparks in a geometry or in a line, make that ignition kernel is larger. You can see that for methane air flames, if you put that same energy in a single spark with a small spark, you cannot ignite it. If you split the energy, make it to 3 with a larger size, and the methane can be ignited. So this experiment also clearly shows that plasma not only can generate radicals, but also can generate a volumetric discharge that allow you to ignite reliably and successfully for lean and low pressure engines. So the geometry design for plasma is very important to enhance ignition. Again, this is the experiment done by Dr. Tim Rambello at Air Force and with Joe Lefkowitz. It says that if you have a flow, for example, in a reactor, you can see how does that the ignition energy and that the gap of the electrode and affect that the successful ignition. So this he played that he says that we played that the frequency of the discharge. At low frequency, you can see ignition kernel, they are decoupled. And they are at a high frequency, they are fully coupled. You can see that fully coupled one has a large ignition volume. They can successfully ignite the mixture. And if you're interested, you can see that if you plot the ignition probability, and if you change with the same energy, if you change the gap, you make that the electrode gap is small, larger and larger. With the same energy, you can see that the ignition equivalence ratio getting lower and lower and lower. So this experiment clearly shows even in a flow, in a ignition with a flow, that ignition size play a big deal in affecting whether ignition is successful or not. Thus indicating that plasma can do a great job to enhance lean burn ignition if you can ignite a large ignition volume. So I'm not going to repeat this again. So Joe Lefkowitz and Ken Carter, they did a beautiful work to measure, do simultaneous measurement about this plasma frequency, and then as a function of time to measure that OH PLIF and with selenium. So you can see that at a high frequency, this OH is overlapping and at different pulses. You can see that this OH production is overlapping, and so that they can ignite successfully. At the low frequency, you can see this OH, they ignited, but then you can see ignited here, they are separate, and eventually the ignition kernel is quenched. So therefore, creating a large ignition kernel is more important than putting a lot of energy. It is not governed by the energy, it's more governed by the ignition volume, okay, for plasma ignition. So plasma can do a lot of good job in terms of enhanced ignition in engines if you understand that the critical ignition radius. So this is an experiment done in the Air Force again by Tim Rambello and Ken Carter, and showing that in the cavity, and they can, by putting the ignition with nanosecond discharge, so can generate large ignition volume so that it can flame spread much faster with a nanosecond discharge with compared with a single second. And the ignition time is also shortened because of the high frequency nanosecond discharge. All right, so, and also that some of you took that the class from Professor Masarsky today in terms of a lean blow off. For example, if you have flame stabilization behind this kind of bluff body, you can see that the inclusive flame, what he says. The other one is that prior to the blowout limit, you can see the flames becomes like an open flame, become inclusive flame, and the flame speed seems the flame become more volumetric compared to the thin flame front. And he did a wonderful job in terms of measuring, simultaneously measuring that OH and formaldehyde. You can see that for a close to the lean burn limit, you can see this formaldehyde formation is increasing and increasing, and when you have large formaldehyde formations, and then extinction happens, or lean blow off happens. Why is that? This is because if you understand the chemistry, right? Flame, stabilization is governed by that the inverse of flame speed, and in terms of dynamics. But it's more importantly that the hydrocarbon combustion is governed by these reactions. this reactions is not only important because that they convert that the formaldehyde into HCl, and this is exothermic reactions. This is also that important reactions for OH production and and oxidation. So from chemistry point of view, this is the dominant heat release reactions of hydrocarbons. Another way that this is also a production about HO2, as I said before, at the intermediate temperature. Once you have a lot of formaldehyde, which cannot be oxidized like this, that means that you don't have enough OH radicals. At that time, that plasma can help you. Plasma can help you to add more OH radicals to accelerate this reaction. And also plasma can help you to enhance flame speed by doing ignition-assisted flame propagation. All right, so that is a way how plasma do enhance flame speed. Number one, and generate more radicals at the near extinction limits. Number two, by promote flame speed causing ignition-assisted flame stabilization. Number three, that create a big volume that ignition becomes overcome the critical radius of ignition limit. So again, I tried using this figure to show that if you do using plasma can enhance that the ignition Dunker number and make that flame speed that is much bigger than the adiabatic flame speed due to the auto-ignition assisted flame in this kind of cavity, in this kind of HCCI engines using plasma, then you have much better limb-burn limit to do that. Indeed, and in our lab, and we try to do this kind of what is a turbulent flame speed as a function of Reynolds number. So what we do, we're using this kind of a reactor-assisted turbulent slot burner. So it means that in this kind of a Bunsen flame, I have a flow reactor, which I can control the ignition Dunker number. As you can see from this figure, the turbulent flame speed as a function of Reynolds number, this is that the chemically frozen flames, that the ignition Dunker number equals 0. If you raise the reactivity from the bottom, you can see that the turbulent flame speed is increased and then become a much higher than the chemically frozen at a large ignition Dunker number. This is because that the plasma or a low temperature associated flame propagation, ignition assisted flame propagation speed is higher than the flame speed of chemically frozen flame. So again, that this is that the I'm not sure it will play. You can see that this, if you increase the equivalence ratio and increase the reactivity by promoting low temperature combustion, you can see the flame flashback will happen. You see the flame, the flame will flash back into the burner. You can see already happened here. So that means that ignition associated flame can enhance the flame speed. It can enhance the flame stabilization. All right, so I try to summarize that what plasma can do. Plasma can accelerate ignition, make this S-curve change. And plasma can enhance that the limb-burn limit by promoting ignition-associated flames and enhance the flame speed. Plasma can enhance ignition engines by create a big volume that overcome the critical radius governed by that a large Lewis number. So with that, I try to conclude what I said, what plasma can do, what plasma cannot do. And so let's take a break at maybe 10 minutes. Let's come back. Right now is 3:35. Let's come back at 45. Okay. Okay. Is that okay with you? Any questions?
Yes, there are 3 questions. First question, dear Professor Zhu, how effective is plasma in the combustion of fire retarding species?
Can you repeat that question? Is fire?
How effective is plasma in the combustion fire retarding species?
Oh, fire retarding species. Okay. Oh, that is a great question. I think that I have not studied that how effective that the plasma created radicals in fire retarded species. And mostly the fire retarded species, just like, for example, something like a toluene, right? So you can grab H radicals and terminate the reaction. So if you have plasma that can break down the fire retarded species, I guess that your fire suppression effective will be reduced because that you are not grabbing a species. Actually, the plasma will break down your molecular structure, generate the species. This is a great question. I should be studied how that plasma affects the chemistry effect of fire retardant.
Second question from Kiang Ching. Hi, Professor Zhu. Could you briefly explain how does plasma affect carbon fuel and carbon-free fuel, such as hydrogen and ammonia, ignition and combustion?
For hydrocarbons, the plasma affects that the chemistry at high temperature. For hydrogen and for hydrocarbons at high temperature, pretty much the same. The plasma generates radicals that affect your chain branching reactions of H plus O2 reaction. For hydrocarbons at a lower temperature, that the plasma can promote low temperature combustion chemistry for hydrocarbon fuels, which hydrogen doesn't have it. For hydrogen, the plasma pretty much enhance that the ignition mostly, that because of the hydrogen is difficult to generate the radical, initial radical, but plasma can, right? But in terms of flame speed, plasma probably cannot help you too much because that is governed by H plus O2 reaction. Unless you plasma create your temperature is so high, plasma can create a ignition assisted flames. For ammonia, I think the plasma can do a lot because that the ammonia is very difficult to be ignited by itself, and because the heat release rate is small for the fuel. Plasma can break down that bond of NH bond and very quickly generate H radicals, which is needed for combustion. So there's a Professor Wenqin Song studies this, but there's very few studies of plasma ammonia assisted combustion with detailed diagnostics of active species. I think this is very interesting topic. Thank you very much.
There is a follow-up question for the fire retarding species. How to select the process / plasma that will break down the radicals in fire retardant species?
I think that the one thing that you have to look at that two things. One is that you have to look at that what is that the bond energy compared to the electron energy in the plasma. So you have to choose that the plasma electron energy in the plasma that can break down the bond, which is critically that control your retardant reactivity. And that is the one thing, and we have to consider it. The other one that is that when you have a control that the plasma, that make sure that the plasma generated that the active species, and they will be terminated effectively by the retardant. So I think this plasma generated species, for example, O2 singlet or O2, for example, ozone. So make sure that ozone will not be reacting with your retardant, accelerate your low temperature combustion. So I think that there are two things, that direct interaction between electron impact, dissociation. The other one is that the plasma generated active species will be terminated by the retardant. I think this is a very interesting area.
Question from Tawfiq Bushaki. Does the plasma increase the flame speed under all conditions, kind of fuel, equivalence ratio, etc., or there are preferences?
So as I said before, flames normally we're talking about hydrocarbon flames and hydrogen flames. They only exist above 1200 Kelvin. At that conditions, the H plus O2 chain branching reactions is so fast. They produce radicals much faster than the plasma can do. In other words, that the plasma can only contribute a tiny amount of radicals, so they don't accelerate the flame speed of flames unless plasma can trigger ignition fast enough. You make the flame is ignition assisted flame. At that time, flame speed, ignition assisted flame speed will be dramatically enhanced by plasma. All right. So at a lower temperature, in other words, if the unburned mixture is very low temperature, plasma has nothing to do with your flame speed. If the unburned mixture temperature is elevated and is more auto-igniting, more like close to auto-igniting mixture, plasma can dramatically enhance the flame speed due to promote auto-ignition assisted flames.
Last question from Dr. Basha. Dear Professor, what is the current advancement in the area of plasma-assisted combustion for biodiesel fuels?
I think that I think that is I'm not really clear in terms of how biodiesel with the plasma areas. I think that the advance of that is mostly probably is that in the chemistry side still, that how does plasma affect that biodiesel chemistry, ozone affected that the biodiesel chemistry. So that is that the most of the frontier research in terms of plasma generated active species. How does the kinetic affect with the biodiesel fuel?
Another question from Matthew Montgomery. If the electron ion temperature distribution in the plasma is tuned, such that it is narrowly centered around a particular value, could certain combustion reactions be selectively initiated or promoted?
This is a great question. And the answer is that they know that the plasma electron temperature is not sitting in the center of some particular temperature. It actually is a non-Boltzmann distribution. You have a very long tail in terms of high electron energy. So you should be able to tune that kind of distribution of non-Boltzmann distribution of electron energy to optimize your selectivity and the reactivity of your mixture. That's the key point of plasma-assisted combustion or chemical conversion.
Okay, thank you, Professor. This is all the questions for now.
Okay, all right. So I will get a cup of coffee and then come back and continue. Thank you.
Yes, Professor.
All right. So this next lecture, I try to briefly touch about this electric field effect. This is a very interesting phenomena, and in terms of dynamics, but it's really not very much applications in combustion, but more application probably in boundary layer control or flow control. But so I will quickly go over with it and then end it as soon as possible. So electric field effect and in plasma assisted combustion or flow control, it is because that when the electric field is not strong enough, there's no breakdown, but it only generates that electric field. So therefore, you have two effects. One is that ionic wind. The other one is that the Joule heating. Of course, ionic wind will change your mixing between fuel and air, will change the velocity, flow pattern, will change your flame geometry, will change your soot emissions because of mixing, will change a lot of things, etc. But from an application point of view, it's not easy to use because the ionic wind is not easy to control and exactly in a combustor. But on a boundary layer or on the surface, the ionic wind can be well controlled. You can dramatically change the flow dynamics using ionic wind. And because of the electric field, you accelerate the electrons, the energy transfer between electrons and molecules will give you some kind of Joule heating. So that can enhance the flame speed, but it's very minimal. So let's go forward. In a flame is a weakly ionized plasma. They have this kind of positive ions, and due to the CH reaction with O, they form, and then HCl with water form this positive ions. The ion number density actually is very, very low, and you can see most of the work done by Calcutt and in 1960s. So if you have a DC field, direct current, then you can actually separate the charge, make the charge, positive charge go into one direction, negative charge go in the other direction. So therefore, that the motion of the positive charge, like H3O and CH3 plus, they will collide with a nitrogen and oxygen in the air. They are generating a motion. If you have AC field, and then that motion basically is oscillating locally, so therefore you don't have a mean flow, but you generate electronic heating. So in most of the plasma, for example, you have a combustion timescale is much longer than the microwave. They are longer than the collision between electrons and and nitrogen. And depending on the AC and DC, you have different timescales. So you should try to analyze what kind of timescale you are working on. And if you're looking at ionic wind, so let's say that you have electric field and you have a charge. And the charge has a force, and in electric field, F equal to charge times the electric field. This will do the work and to accelerate ions. That ions will collide with neutral molecules to generate a velocity, a drifting velocity or ion wind velocity, which is proportional to the energy and by that the electric field. And for example, if you have a positive ions and negative ions, and their molecular weight are almost comparable. So you can say if you have electric field, the positive ions will go to that direction, and then the negative ion will go that direction. And they have a similar magnitude in terms of velocity. But if you have electrons with a H3O plus, this one is much heavier. If this one move to that direction, the electrons will have to follow to that direction as well because of the charge separation. You have to make the charge is neutral. So therefore that the speed of negative ion will be very low, and then the speed on positive ion will be higher. So it's unsymmetrical. This generate a lot of interesting phenomena in early days, for example, and this is the early study by Calcutt and Weinberg. They see that if you have a put an electric field and with different kind of voltage, and in an open system, you can see there's a flow induced to the positive electrode and negative electrode. If you put it in the how close to the system, you have a circulation because of the closed cycle. If you have a lighter and charged particles, and the flow will be unsymmetrical, and you have a flow moving to one direction. So this kind of very interesting, fascinating phenomena, and even published in Nature. And they can dramatically change their flame shape and soot emissions. And Professor Min-Soo Char is one of the leaders in these areas. And this is an experiment from his experiment, basically showing that you have a flame, Bunsen flame, you have electric field, and you put a laser to imaging the flame. You can see this is the current, and this is the flame shape by putting a negative charge. And the negative charge, that means that the electric field is going to that direction. So the positive ion will move to this direction. Your flame shape, it looks like that. You're pointing to the right. You put a positive charge, and the positive ion will move to the left, and the flame will link to the left. And same time, if you have non-predictable flame, you have form a soot, and you can have a more significant phenomena because soot particles are easily to be charged. So this is very interesting in terms of geometry. And also that Professor Char did a lot of diagnostic studies about that Bunsen flame flow imaging. For example, this is that vertical imaging. This is looking from the top. You can see the flow field. One goes to the left, there one goes to the right, and negative and positive ions. And so depending on the voltage. So this is a flow field imaging. This is that the positive, negative ions and positive ions that go to different directions. You can see the flow field. Very beautiful pictures and very interesting in terms of phenomena. And also in countable flames, if you have no plasma, and then you have flame sitting here, you have a flow going from that to the one nozzle to the stagnation flame, and the other one also goes to the stagnant flame. But if you have a electric field, ionic wind, you are forming a two stagnation flame, because that in the flame you have positive ions go to let's go because the negative charge. So therefore the positive ion will go this direction, and negative ion will go that direction. So you will form a stagnation flame, one stagnation here, another stagnation here, and then in the middle you have a flame. So just like this figure. So because that you have flow generated by ionic wind, that the positive ion goes in that direction, the flow from going in that direction. So you have one stagnation flame, and there's another stagnation flame here, and then you generate the entrainment of the flow to that direction. So this is a beautiful picture showing the dynamics about the effect of ionic wind. And you can also see a lot of things by doing imaging about, I don't want to spend a lot of time here. It's more phenomenological. And so Professor Chow also studied this age flames. You can see that if you put a negative or positive, and then this flames were bending towards that the different side of the stagnation plane. And because of the ionic wind, that this kind of triple flames, they deviate from the stagnation plane. You create a lot of heat losses due to that, convective heat losses. Your flame speed will be reduced, no matter whether it's a positive or negative charge. So this experiment clearly show that your flame speed actually with 0 voltage, you have a higher flame speed, and then you have when you no matter whether it's negative or positive, your flame speed is decreasing a little bit due to that the convective heat losses. So you can do a lot of details, but it's more because of the fluid field modification by the ionic wind. I don't want to touch too much. And again, that you can using this, for example, with different ionic wind, you can enhance that the mixing between fuel and cold flow that reduce that the soot emissions by doing this. You have a strong streamer, a weak streamer, and brush is because that the ionic wind strength. It's all because of mixing. So from dynamically, it's very interesting. From a chemistry point of view, it's not interesting. But for flow control is very interesting. For example, if you have boundary layer, in the boundary layer, because the flow velocity on the wall is 0. But if you generate this kind of a discharge along the surface, create a ionic wind along the surface, so you can trigger that the inverse flow velocity and trigger that flow separation at that point. They can dramatically change that the flow separation in a boundary layer and change that the drag of so a lot of studies are using ionic wind to control that the flow boundary layer velocity profile. That is very interesting in that area. And also, people try to, for a Bunsen flame, you can put that the 2 kilovolt there. You can see that ionic wind and moving from the top to the bottom. You can create this kind of flame shape is going to be changed because that the body force enforced by that the ionic wind. So you trigger that the flame instability or change that flame curvature and surface area. So it's all interesting in terms of flame geometry. And so this is the experiment by Air Force, Bishkanguli, a long time ago. And see here is that Bishkanguli basically showing that it's a Bunsen flame. You put a grid of electrode and the flame shape will be changed. So I think that is mostly because that is the ionic wind effect and also instability. And if you think about that, the flame instability, and this is hydrodynamic instability or Rayleigh-Taylor instability. If you have a new forces causing by this charge, you create a new force field. This force field will increase that your growth rate of instability, makes the flame like this. At Princeton, Professor Myers and I, we try to understand how this electric field affects the flame propagation. We have a countable flame set up in a cavity about a microwave. We send a microwave at 2.45 gigahertz with about to 2.6 kilowatt. You can see the flame front is moving upstream that due to the electric field about this microwave. No breakdown. So the mechanism of this is because of the heating. You can see that by using strong different equivalence ratio with a microwave, kilowatt, you can enhance flame speed by 20 to 30%. It's not a big deal if you put this much about the energy into it, because if you do the measurement by filtered Rayleigh scattering, you can measure that the temperature rise due to that with microwave. This is because that the microwave gives the energy through Joule heating. The flame temperature is increased by 80 Kelvin. So therefore, flame move upstreams and flame speed is increasing. So most of the flame speed increasing in electric field is due to this Joule heating. It's just dumping energy into flame front. So I thought this is, is not interesting at all to me. So we stopped this project but let you know, this is what I try to summarize. The two effects, ionic wind, they change that the flow velocity, mixing, and then instability, and makes the flame shape different, and NOx emission and soot emission are different. But no game changer in terms of chemistry. But as a game changer in terms of boundary layer, I can change boundary layer speed, which makes that flow separation different. And also that can cause in that the Joule heating that raises the temperature and makes the flame speed a little bit faster. So this is pretty much that electrical field effect on flames. Any questions?
Yes, we have one question. Professor Zhu, I would like to ask about the effect of plasma frequency on the combustion. As you presented in your slides, as the frequency increases, the coupling can be observed, but how can one determine the suitable frequency for a certain setup? Isn't the frequency of plasma dependent on the resonance frequency of the system? And is there a way to find the best frequency?
Good questions. I try to answer in this way that the plasma frequency is governing that the electrons. And if you think about the ionic wind, for ionic wind, the higher the frequency, the ionic wind disappear, right? So if you want a ionic wind, you want to have play a big deal. You want to have a very short frequency, or using so if you want to have a Joule heating to play a very important role, that you want the electron to oscillate around the flame front, you want to have a high frequency. So this really depends on their applications to do so. Is that okay with you? All right, so let's see that we continue. I got a lot of materials to teach, and I thought it's 5 days, and actually it's only 3 days. So I have to accelerate. And okay, so
we have one question only.
Go ahead.
Okay, question from Moses Paul. Can you please explain about the effect of electric field frequency on lifted flames?
Oh, okay. So if you have a lifted flames, and the lifted flames, you can see that the fuel and air mixing is very important, because that your flame is lifted. So, and you have a long distance. So the plasma frequency, and I think that probably is a DC and or pulse DC probably is better than any kind of AC. The low frequency probably is much better than the high frequency.
Thank you, Professor.
All right, so let's move on. So I have several chapters in the talk. So, and now we try to the difficult part. It is that what is that the chemistry and that of in the plasma assisted combustion or chemical conversion. So what I try to talk today is that what is the important chain initiation and branching reactions in combustion, and how does that compete with plasma chemistry in terms of electron impact reactions, excited reactions of laser pointer. Okay, and then vibrational excited species, and then ozone nitrogen chemistry. So if this cannot win, then plasma has no chemistry effect. If this can win the key chain branching reactions or initiation reactions, plasma can enhance combustion process. Then we talk about the plasma chemistry and the time scales, and what is that the plasma chemistry on combustion. So this is a very important part, and more depth in terms of chemistry point of view. If you're looking at a combustion and looked at Professor Philip Dago, they will tell you that, okay, the combustion starting from chain initiation. You have a fuel with oxygen, a fuel with H2O2. They give you a few radicals. These reactions typically is very, very slow. So if these reactions are limiting you, for example, ignition of hydrogen, because the radical production is very slow, and then plasma play a big deal role to give you radical bypass this chain initiation reactions, right? And then after the initiation, and then chain branching take over. So at high temperature, 1100 Kelvin, this H plus O2 reaction is dominant. They are very fast. If this reaction is controlling and then the plasma has a little chance to do. Okay, if this reaction is controlling, plasma have a great opportunity. For intermediate temperature, and this reaction is dominant chain branch reaction, plasma can win. Okay, if for lower temperature, if this temperature is you are interested, and the plasma can dramatically do great things for you. So before you start your problem, whether combustion can do or not do, try to look at that whether plasma can win this kind of key reaction rate. And for example, in plasma-assisted combustion, the plasma can collide with oxygen and generate atomic oxygen. They can bypass this chain initiation and give you 3 radicals immediately. And then if plasma can electron collide with oxygen, generate O2 singlet, this reaction bypass this chain branching reaction can also help you. But unfortunately, this species always be quenched by some other species in combustion system. So even though they are fast, but so far there's no experimental evidence saying that this reaction is going to play a big deal to bypass this high temperature combustion. But this things is going to be win in terms of this chain branching reactions because they are much, much faster. So let's summarize what is going on in terms of plasma in air. So you have a plasma in air. You have electrons, they collide with nitrogen. They can electronically excite with nitrogen and go to this electronic state, a B state and a C state, whatever. They have very high energy. You see that around 9 eV to 10 eV. So this guy, they will collide with oxygen, they generate radicals or generate NOx, and these radicals will collide with oxygen to form ozone. And then they also vibrationally excited nitrogen, and this vibrationally nitrogen that can also generate radicals. For fuel, electrons collide with fuel, they break down the fuel into vibrational excitation and radicals and other things. With oxygen, they can dissociate oxygen into O and O singlet D, and these will react with fuel, generate OH radicals and fuel radicals. And also with electron collide with oxygen, generate O2 singlet delta, and these accelerate reactions. All these things generate new reaction pathways is unfamiliar with combustion. For example, electron impacts with fuel molecules, electronic excited nitrogen, O1D reaction with fuel radical with O2 singlet, and it's not clear what the reaction rate is. Ozone reaction with fuel, so many things we don't know. So therefore, plasma really that create a lot of new reaction pathways for us to study in plasma-assisted combustion and chemical processing. This I talked before, that is done by Professor Laux, that with a nanosecond discharge, and he measured that the nitrogen excited states and then atomic oxygen formation, that give him a confidence to conclude that the atomic oxygen generation through this electronically excited nitrogen is the main reaction channel in assisted combustion. That means O is mainly produced by nitrogen BC states, electronically excited, and form 2 oxygen. So this is one conclusion. So therefore, by repeating what I said before, with this kind of plasma generated this species that produce a lot of active radicals and vibrationally and electronically excited things, they couple with combustion chemistry. But this reaction pathway is well understood because they are already in combustion. But these reaction things are poorly studied. Few people really know what is that accurate reaction rate. So they are providing you a lot of opportunities to do experiments to understand the reaction pathways. And this is quantum chemistry. We know that the reaction rate is proportional to that the activation energy and the partition function of the reaction complex and the partition function of reaction and product. And then if you have a plasma that can generate this vibrationally excited states and electronic states, your activation energy is changing, your partition function is also changing. Therefore, your reaction rate is changing also. And then what kind of time scales are you talking about in plasma chemistry? In plasma, we have, ions and molecules, and they have so 10 to is a picosecond to a millisecond. Combustion is somewhere here. It's about from a microsecond to about a millisecond. And the plasma, we are talking about the picosecond to microsecond. They're involving with ions and molecules, electrons, and involving distribution functions of electrons, involving interaction between plasma generated species with a combustion species. So this is very complicated. So a lot of studies, for example, in this kind of a plasma timescales is talking about here, has been done in air. But with the fuel appearance, very few studies has been done in terms of plasma chemistry. Combustion chemistry has been well studied, but the connection between plasma chemistry with combustion chemistry is poorly studied in this region. All right, if I say somebody wants to do this, do something at low temperature rather than do something at high temperature. At high temperature, plasma does not matter anyway. So do something study in this region is very interesting, and you can publish good papers very quickly. So to look at the oxygen. So oxygen, if you look at the energy states and in terms of inter atoms diameter distance, so the lowest excited states of oxygen is O2 asinglet. Is only require 1 electron volt, probably 0.98 electron volt. The next one is oxygen B state, is somewhere here, and is oxygen B state. That is only 1.6 electron volt. And if you have high electron energy, you can excite the O2A state somewhere here, and which is 4.5 electron volt. You can excite that the pi state and B state, that's higher. These electron excited states, they have, the energy is so high, 12, 5.6 EVs, 8 EVs. They are very energetic in terms of reactivity. So if you're looking at the cross-section area, that's indicating that reaction rates for electron impact reactions, you can see at the lower electron energy, below 1 eV, most of the excitation of oxygen are rotational excitation, vibrational excitation. But at the 10 eV, you can start to see that the excitation of O2A states, O2B state, and then you have the dissociation and singular oxygen production, singular DS production, and even ionization, 13. So most of the non-equilibrium plasma, they have that electron energy above a 2 electron volt. Actually, in this region, they generate a lot of this excited states. That's a complicated the plasma chemistry. If we look at nitrogen, so nitrogen has, ground state is here, a sigma state. They can excite to A states at 6.2 eV, that B states at 7.3 eV, and the C states at 11 eV. So this excitation give you very high electron energy. So this kind of ABC states, then when they collide with oxygen, and they're likely to break down oxygen into atomic oxygen to enhance combustion. So we're looking at energy state is here, and ABC state. So if you're looking at hydrogen oxygen mixture, and the question asked that today a lot of interest in hydrogen. So you can see at the lower electron energy, you are exciting that A state and rotational and vibrational oxygen. But at a high non-equilibrium plasma, you start to dissociate, you can generate this ionization. So vibrational state is not excited at a very high electron volt. So these kind of things, you have electron impact with nitrogen, generated nitrogen C state, nitrogen C state reaction with oxygen, generate 2 atomic oxygens, and this direct dissociation of oxygen. So, and also that if you have generated vibrational nitrogen, let's say vibrational nitrogen, the peak around a 30 to 40 constant. So at a lower electron energy, you excited the nitrogen state. This nitrogen state can, for example, reaction with H2O2 and they generate vibrational H2O2. This vibrational H2O2, they can generate H radicals, or they react with alkyl radicals. They accelerate that the reaction rate of alkyl radicals. So this is give you a new reaction pathway in a plasma. Another thing that this is from Andrei Starkovsky and Princeton. He gave me slides that about hot atoms. For example, if you have electron impact, you generate this with oxygen. You form a electronically excited state of oxygen or electronically excited hydrogen. So when this electronically excited state of oxygen and hydrogen, they dissociate, they form a atomic oxygen, but p state, triple p state, and 1d state. But they have more extra energy. This extra energy has no place to go. They make this oxygen is very hot, means that have very high translational velocity. So this oxygen even is at triple p state, a ground state, but they have very hot. They are not a equilibrium with your temperature locally. So this hot electrons, they can change hot atoms. You can change their reaction rate, and this is that the cross-section areas of hot electrons between hot H with hydrogen, the hot H with oxygen and methane, and computed. And to what extent this model is valid, I don't know. No one can answer this question, but physically it is there. And gas heating. And so, for example, if we have a electrons, we combine with oxygen ions, they generate two radicals, which is great. But at the same time, they give you additional energy because this energy is this is too energetic, and these two excited state of, and they cannot absorb all the energy. They have to give additional energy. This energy is fast heating. Ion-ion recombination, electron-ion recombination, and excited nitrogen dissociation, and excited oxygen dissociation. They all generate additional energy in a nanosecond time scale. All right, fast heating. And slow gas heating, that basically that have a higher vibrational nitrogen that collide with a molecular, and then my vibrational state is going to be reduced, and I give you the energy. So these are the fast gas heating and the slow gas heating in a nanosecond, in a micro to millisecond time scales. So this has to be considered in terms of plasma modeling. So if you're looking at the gas heating power refraction with more oxygen involved, because all these kind of reaction and the involved oxygen, you have a fast gas heating ratio is increased. So higher oxygen, you have to consider faster gas heating more accurately and in modeling plasma assisted combustion. So in summarizing that the plasma chemistry is much, much more complicated than combustion chemistry. When somebody say combustion chemistry is complicated, but plasma is 10 times more, because they involve this kind of a non-equilibrium reactions by ions and excited states. And the reaction rate is not only a function just by temperature, but also by electron temperature. So, and even vibrational temperature. It's too complicated. Now you have ions chemistry, and you have electron-ion recombination, ion-ion recombination, molecular ion reactions. You have electronically excited species reactions. You have a hot atom reactions. You have a fast heating, slow heating. You got a lot of excited states, and very, very complicated. And that's why we want to study it, because it's so complicated and so useful. And in terms of combustion, the reaction way and reaction is coupling is that we can see this kind of vibrational states because the same time scale. And they affect your reaction pathway, because once, for example, if nitrogen is vibrationally excited, the reaction with water, they maybe break down the water particles. And the vibrational studied nitrogen, they are not inert anymore. They can collide with alkyl radicals and then form a radicals. And the same is here. This reaction rate will be different from the ground state. And for example, nitrogen vibrational state with H2O2, they can transfer the energy to vibration of H2O2. Then if the H2O2 react with methyl radicals, CH3, they're going to accelerate the reaction rate. So these kind of vibrational reaction pathways also affect that the combustion chemistry. I try to highlight some of the reactions, and we talked before. You have electron impact associated reactions and vibrational excitations, electronic. They generate radicals, and they generate a faster the non-equilibrium excitations. You have this kind of ion recombination, attachment, charge transfer. They not only generate you radicals, but also give you heat. And then you have this kind of excited states, and they give you radicals, fast heating, slow heating, all this kind of important things. But which reaction is important? But that is easy for you because that combustion progress develop a lot of tools for sensitivity, for reaction path fluxes analysis, for whatever things you want to do. And you can, as long as the reaction rate is accurate, and you can identify which reaction is important. But the main thing is important is the reaction that generates radicals and chain branching reactions, always, and fast heating. So look at, again, this figure that, okay, and plasma generate a lot of species. And these species has different time scales. They generate stable species, well, for example, NOx, ozone, fuel, whatever. They have a long time scale. They generate radicals and metastable species. They generate this kind of excited species, and they are very reactive. They also generate electron ions. The question is that how does this thing is going to affect my combustion, right? So this is the questions. A long lifetime species, how do they affect combustion? And excited species, how do they affect the reaction rates? So this question has to be answered and in combustion. So let's take a very simple look before we try to understand. So let's say that I have hydrogen and oxygen combustion. I know that in hydrogen oxygen combustion, the dominant reaction, chain branching reaction is this. H plus O2 generate OH and O. As you can see from here, so this is at the reaction rate constant. And then you compare the reaction flux. That means how much radicals is generated. You compare to all these important reactions, H plus O2 reactions, hydrogen peroxide reactions, and the chain initiation reactions. You plot in this figure. You can see that this plasma generated radicals, electron impact oxygen at very high electric field. They cannot compete with H plus O2 reactions above maybe 1300 Kelvin. So that means in a flames, which is burning above 1300 Kelvin, this plasma reaction, they are much slower compared to the chain branching reaction by flame itself. So therefore, plasma normally does not have a big impact in terms of a high temperature flame speed. However, if that the reaction at intermediate temperature is governed by this reaction rate, you can see this plasma generated radicals is much, much faster than that at almost the entire temperature of combustion. So if this reaction is limited, you got a great chance. For ignition, for hydrogen ignition, and the chain initiation reaction is difficult. So at the almost entire reaction range, plasma can provide radicals much faster than the chain initiation reactions. For ammonia reactions, probably the dominant reaction is also below this, and plasma has a great opportunity to accelerate ammonia combustion as well. So this diagram is very important to tell you why that the and why and when that the plasma can affect the chain branching reactions in combustion system. So let's look at that the one species like O2 singlet. We're looking at that the ground state, that the sigma state is H plus O2 reaction rate, and this is here, okay? Below, we're looking at below 1500 Kelvin. If you're looking at H plus O2 A singlet, and for radical production is this line, there are 2 orders of magnitude faster than the H plus O2 at the ground state reaction. So therefore, if you can, theoretically, if you can produce is O2 A singlet by plasma, you can accelerate the chain branching by 2 orders of magnitude if this is not quenched. This is very interesting. Now, if you're looking at that, the chain initiation reactions, this is the ground state, the methane with ground state oxygen. And this is at the oxygen singlet. You can see that you are enhancing almost by 5 to 10 times by producing singlet oxygen. If you look at the CO oxidation, again, that so ground state in terms of singlet state, and the reaction is 1 order of magnitude or 2 order of magnitude higher. So if you're looking at the radical production with a lower electron energy with high electron energy, and you produce a lower electron energy to produce 2 O atoms. At high electron energy, you produce one O atom, 1 O singular delta. This singular delta is very reactive. So you want to produce more singular delta and then produce just a ground state of oxygen. So you can see from chemistry point of view, plasma indeed can give you opportunity to accelerate that the rate limiting reactions. So let's say that how O1D singular delta affected my reaction. Again, this reaction is the dominant, is one of these chain propagation reactions. The reaction rate is about 6 to the 10 to the 11th if you're looking at the chemical kinetic model. But if you produce O1D and the reaction with hydrogen, they can produce the same product, but the reaction rate is 2 orders of magnitude, 1.5 magnitude, 10 times higher or 20 times higher than this one. So even at grounds, at 300 Kelvin. So therefore, you produce this guy will immediately react even at room temperature, give you radicals. So this is a very interesting result. If you're looking at a O1D reaction with methanol, and they can, even at a very low temperature, they can generate this kind of a very complex intermediate species and generate you radicals, for example. And the O1D reaction with methanol, they can generate methanol radicals plus OH, and also can generate HO, plus 2 OHs. This one generated 2 radicals, this one generated 1 with a methanol radical. So how do we determine that the reaction pathway? So O1D reaction with fuel is a multi-channel insertion reactions. That means O atoms not only just attract H atoms like a combustion, but they can insert, you can see this is an O atom, they can insert that the CH bond between the C and H and here, and make insert into the molecules, and then make that the reaction channel more complicated. But very few data available. If you can measure this O1D reaction with fuel, and you can publish a paper very quickly. And so this is the reaction we talked before, is the ozone reaction. And although we did this ozone reaction with biodiesel, with some of these ethylene, but there are many other reaction fuel we have not done about ozone reactions. So they can promote low temperature oxidation. From here, you can see the ozone oxidation. And this, ozone reaction at very low temperature, they produce a lot of intermediate species, and like ethanol, like ketenes, like hydroperoxide species. So so this is ethylene, but what about other unsaturated hydrocarbons? And very few experiments are available. And if the plasma generates this kind of quick intermediates, and this quick intermediates and can be inserted into water, can be inserted into acid, can be inserted into alcohol, can be inserted into hydrocarbons. And they can be continually inserted into make these particles bigger and bigger. That create a aerosol formation. So understanding that this quick intermediate formation in plasma or in ozone help you understand that the pollutant formation or aerosol formation in forest and also in a upper atmosphere. So this reaction channel is not well understood as well. And then plasma, as I said, plasma generate NO and NOx, and this NOx can modify your RO2 chemistry, and it can slow down your low temperature chemistry, and can enhance your intermediate temperature, right? So this is something we showed you before. With without a NOx production, this is that the endodecane oxidation, low temperature chemistry, and intermediate chemistry. With a 300 ppm NOx addition, you can see that low temperature chemistry is slightly delayed, but intermediate temperature chemistry is dramatically accelerated. So understanding the low temperature chemistry of NOx and the intermediate temperature chemistry of NOx reaction is also important. And also plasma effect into NO. So we did some experiment in last symposium paper that we can say that we endodecane, 1% endodecane in air and with 1% endodecane fuel. In the air, when you increase that plasma frequency, you can see that NO is increasing because that the plasma assisted a NOx formation. But if you input 1% of endodecane into it, you see that NO almost disappears. See what I'm saying? So you can see that there's no NOx formation. This is because that the NOx formation, NOx formed in the plasma, they're going to be reaction with low temperature chemistry stimulated by the plasma, the conversion NO2. That's why you cannot see NO. Does not mean that you don't have NOx. All this NO becomes NO2. And at the same time that Professor Wan-Tin Song is saying that using plasma ammonia combustion, he sees a lot of NOx is dropped. I'm not sure this is whether that this NO2 is measured. If the NOx is dropped, maybe due to low temperature chemistry, they convert it. So there's a lot of interesting things in this kind of a plasma affected that the species. This is a figure we just talked before, and plasma can dramatically enhance this low intermediate temperature and low temperature combustion. But this, how does this active species interact with this combustion chemistry at the intermediate temperature and low temperature is poorly understood. This is basically that schematically saying that I showed you before, plasma chemistry can couple with a high intermediate low temperature chemistry and an accelerated ignition process, accelerated low temperature chemistry much more than high temperature chemistry, and make that ignition S curve change dramatically. So this is that the demonstration we showed you also before that the plasma can generate ozone, can enabling that the cool flame formation at a very low temperature. So I don't want to repeat it anymore. So this is something I want to share with you that plasma, the key plasma chemistry, and they can affect that the combustion process. They can affect the aerosol formation. They can affect the NO emissions, and many of these reaction pathways are not well known. So I try to stop here and take some questions.
Okay, maybe we covered that, but Professor, question from Peter Zhu. Since plasma could activate nitrogen, how does plasma change the NOx profile in a flame?
Oh, that's interesting. I think that, as I said before, plasma can increase the NOx formation, and the formed NOx can react with a RO2 and in hydrocarbons, and they convert this NO into a NO2, and then eventually the N-containing species will be still there. They probably increase the NOx formation in most of the case, until you have some kind of ammonia process and maybe in with nitrogen activation, you can, at some kind of condition, you probably can reduce NOx emissions, but in most of the case, probably enhance. But in ammonia combustion, you probably can reduce NOx emission due to that, the catalytic, selective NOx reduction.
Another question, is there any software support for plasma combustion mechanism modeling, or is there any detailed kinetic model with plasma has been published before?
Excellent questions, and we will talk about tomorrow.
Okay, thank you, Professor. This is all the questions for now.
Right, so let's continue. So let me continue to talk about this. Next thing is that the diagnostics, and the really in last few years that the major progress in plasma assisted combustion and is that the diagnostics methods of plasma. So let me share the screen with you. Maybe which one is this one? So we still have 40 minutes. Is that right? If you want to take a break, and can we take a 5 minutes break and come back?
Okay.
All right. Go ahead to take a 5 minutes break, and then we come back. All right. So we are next 45 minutes. We discuss about the diagnostic method for plasma properties and plasma chemistry. So we'll talk about three things. At first, we're talking about the measurement of plasma properties, and including electron number density, electron temperature, electric field, and then we are discuss about the diagnostic method to measure key active species, so that we understand the kinetics, and then non-equilibrium, for example, vibrational temperature, rotational temperature, and then non-equilibrium process. And we talk about the multi-species diagnostics and try to develop a chemical kinetic model for plasma-assisted combustion or chemical conversion. So let's start to talk about the measurement of plasma properties. The first thing is that is really important is that how to measure that the plasma properties, because the reaction rate in plasma-assisted combustion is not only the function about the gas temperature, but also that important is that the electron temperature. And in terms of plasma, that the energy is coming from electric field, and that energy and electric field accelerate the electrons, depending on what is the electron inner temperature and what is the electron number density, what is the electric field, and then the ions, radicals, excited species produced are completely different. So therefore, quantitatively measure that the electric field and electron temperature and number density is extremely important to develop a predictive model for plasma-assisted combustion and chemical reforming. And fortunately, that in the last few years, a significant progress has been met and in the diagnostic of plasma properties. And nevertheless, and very few experiments have been done to measure all three parameters altogether as a function of time, as a function of spatial resolution. All right. So let's say the first thing we talk about is that the Thompson scattering. So Thompson scattering is a elastic collision scattering, not collision, sorry, is a elastic scattering about accelerated charged particles like electrons by electromagnetic radiation. In other words, if you have a laser beam and which oscillating electric field, that electric field is going to accelerate electrons. And when the electrons is accelerated by the photons, they're going to scattering your signal. And so this is a laser beam, and in the vertical direction, you have a oscillating electric field, polarizing electric field. So electrons will be scattering this laser beam into different directions with an angle of theta. The power of scattering in Thompson scattering is proportional to functional to that what is the angle between the laser beam and then the scattering directions, and what is that the angle between that the polarized electrical field and to that the plane of laser and then scattering. So this is the plane of a laser beam and scattering direction. and that the angle between that's the polarized electric field to this plane is a phi. So this a scattering is a function about between a theta and a phi in this reaction. So the number of photoelectrons and during the scattering is proportional to, of course, the number density of electrons and the size of imaging size, which is delta L. And then the eta is optical efficiency, and that the laser energy, of course, the higher the laser energy, have more scattering signals, photons. And more importantly is that this a Thompson scattering cross sections as d sigma e d omega is defined by here. So these are a lot of parameters here: the optical efficiency, the length of optical length, and the electrical field. And in order to remove this, is often that normalized by the Thompson scattering, by the Raman scattering. So you took that the ratio about this the signal of Raman scattering, which is proportional to the similar to this eta and the delta L and also the EL. So you can cancel these things and cancel this H0. The only thing left is that your intensity of the Thompson scattering, and then the cross-section area of Rayleigh scattering and Raman scattering. If you pick up a particular molecule like that in nitrogen, and you can obtain the electron number density by taking the ratio of Raman scattering with a Thompson scattering, canceling this other constants. So this can allow you to measure electron number density by this Thompson scattering and Raman scattering ratio. And also that when you have electrons accelerated and in the electric field, and they move towards or against that the laser beam, they generate the Doppler broadening. So if you measure that the Rayleigh scattering and the broadening about the signal and using Doppler broadening, and the Doppler broadening is a function about the speed of that of electrons. The speed of electrons is a function of electron temperature. So therefore, by measuring that the broadening, Doppler broadening, you can measure the electron temperature. And for example, you can set up this and that Princeton in my lab, and Tim Chen, my graduate student, I hope to set the Thompson scattering. You have a Yiguang laser generated 532 nanometers with about a half joule per pulse. And then you generate this into this kind of reactor. This is a plasma reactor. And so when you have plasma discharge, and then this is a Thompson scattering signal will be collected through this because it's elastic scattering, and so it's at the same frequency of the laser beam. You using a spectrometer and to record the signal and to block that using a needle to block that the original laser signal. You can measure the broadening. For example, you can measure that the Raman scattering about this rotational transition. And you can also subtract that these, you obtain the Thompson scattering by subtracting this Raman scattering. You can see this is that the summation of Raman scattering and Thompson scattering signals. If you, without plasma, you obtain this kind of Raman scattering. And if you subtract them, you obtain this kind of green distribution. This is, and by blocking this original 532, this is the broadening. So electron number density was proportional to that the area under this curve. And the larger this area, the higher electron number density. And the electron temperature will depend on the broadening, that the delta lambda. And so this higher the delta lambda, the higher the temperature. By doing this, you can obtain two things together: number density of electrons and the temperature together. So let's show you the result. This is the result obtained by Tim Chen, and with a 60 tall with argon with 50 hertz pulsed frequency, 30 nanoseconds, 90 millisecond resonance. You can see this is the 30 nanoseconds and the plasma discharge. You can see that the electron number density is built up, and even afterglow, and it's continuing that the generate electrons as a function of time. This uncertainty is large is because that the signal noise ratio is small. Now we improve it by improving the optical efficiency. So the electron temperature, you can measure that just right after the plasma discharge. You have the mean electron energy is about like 3.5 or 3 between 3 EVs, and then decay very quickly in terms of nanoseconds. That's what I'm trying to say, that the plasma process is a nanosecond timescale and remain at about half EV for quite a long time. So this is very important, that the properties of plasma before you start to model and that process. But if you have a methane, if you add a little bit of methane into helium, for example, you wonder that whether that they will affect that the electron number density and temperature linearly. By measuring this electron density by adding 1–2% of methane into helium. So what do you see? You see that by adding 1%, that the electron number density drops significantly. By adding 2%, you can see that they drop a little bit. So this result is for the first time demonstrate that adding methane into helium causing not only that the drop of electron number density and electron temperature, but also this drop is a nonlinear decay. In many previous plasma papers, people argue that by adding 1 or 2% of hydrocarbons into argon and helium, you're not going to change that electron temperature and electron number density. But this is the first time the results show that no, it does change, and it does change non-linearly. All right, so this is a very important evidence of in situ laser diagnostics about how hydrocarbons affect the plasma properties. And at Ohio State, Professor Igor Adamovich is one of the leader in this area and measuring that Thompson Scattering, measuring electron number density, temperature, and electron energy distribution. So one of the experiments he did is that he measured that electron number density and temperature with the helium at 200 tall with a pin to a sphere discharge. And using using the Thompson scattering by blocking this 532 nanometers, measuring electron number density and distribution function. So this is that Raman signal. By taking the ratio of this Thompson scattering with Raman scattering, you measure that the electron number density. So here that the result with 5% of hydrogen in helium. And this is that the signal we measured. So the broadening indicating that the temperature of the electrons and the area indicating the number density. So what he measured that the electron temperature about 2.0 EV and the electron number density is 10 to the 14th. That is quite high in terms of electron number density because it's helium. And if you look in the oxygen helium, 10% oxygen helium, you can see that the electron number density is dropped by order of magnitude, because the electron like to attach to oxygen, and the electron temperature is also dropped. And so this again showing that is very critical to measure that how electron number density and temperature depend on that the reactants, hydrogen, methane, and oxygen, they all affect that the electron temperature and the electron number density. And they also measure that the multi-pulses. He measured 2 pulses. You have 2 discharge at 400 nanosecond apart. We have 1 plasma discharge, another one, as separated by 400. You can see that this is the electron temperature, and this is electron temperature. You can see that the electron temperature drops dramatically between in probably 100 nanosecond time scale, and but the electron number density you still have some residue and between that 400 nanosecond. So this it tell you how that this a repetitive nanosecond plasma discharge is going to change your electron number density distribution with multiple pulses. And so the next thing we try to show you is that how to measure electrical field. We now know how to measure electron number density and temperature using Thompson scattering. And the next thing that is electric field. So we have to measure electric field. Otherwise, we don't know that the plasma chemistry. And so to measure electric field, a method developed at Princeton by Arthur Dagorio in 2017, using that second harmonic generation. So if you have for example, a molecular, and if the molecular is subject to very strong electric field, something like a picosecond laser or a femtosecond laser, and the electron cloud orbitals will be polarized. And for polarized molecules, if you put the electrical field, and that oscillation will generate the second harmonic will be generated due to this unsymmetrical polarization of electrons. So therefore, the second harmonic signal is proportional to that a third order nonlinear optical process. The polarization induced by that the high electrical field for that the second harmonics is proportional to the number density of the gas, and that the third order nonlinear susceptibility of different polarizations, IJKL, and applied electrical field, and then the polarized electrical field of the molecules. And you can derive this equation and showing you that the second harmonic and the intensity is proportional to the square of the laser beam, because this is a nonlinear process, is proportional to the square of the electric field and number density of that the molecules with a constant. So therefore, that by measuring the second harmonic of a molecular, and knowing that the laser intensity, and then knowing the number density, and you can calculate that the electric field by using, this can be done by calibration. For example, if you have a normalized femtosecond laser electrical field measurement for different air, argon, methane, and everything, and you apply electric field, you can measure this signal, and using this signal as a table for calibration, and then you can back up that to measure that the electric field in in situ plasma discharge. Assume that the composition does not change dramatically, because that the second harmonic is mostly proportional to the major species. And then the experimental setup of this e-fish, this figure prepared by Tim Chen, basically saying that you have a femtosecond laser, you're using laser focusing lens, and focusing to a beam west, and in the reactor, DBD, this is nanosecond DBD, and you put an electrode and generate electrical field. As the second harmonics and the original beams will be separated by a prism, and this is that the using photodiode to detect the laser energy, and separate that the second harmonics will be measured by ICCD camera with a bandpass filters. So this experiment is set up and at Princeton in my laboratory, and also in Arthur Dagura's laboratory, and welcome to visit us and to take a look. And this is that basically is that you apply electrical field, you apply an electrical field voltage. This is that you, and this is what you measure electrical field. You can see, um, so the applied field is like this, and you measure the field is like this. This is because that once the plasma is discharged, break down, that the sheath will basically that they share out that the electric field. So your electric field is dropped dramatically once the breakdown happens. So this means that this is a good calibration about this measured electric field with applied electric field at that the rising point of this plasma pulses. And this is try to combine these two things together, combine that Thompson scattering with E-fish, so that allow us to measure that the electron number density with electric field together. So here is the measure the results by Tim Chen, and you see the electron number density, which is that something like this. And you see that the electrical field, and you have a breakdown in this region, electrical field rise a lot, and you have some kind of this maybe reflection, and you have a residue electrical field because probably due to the surface charge that drive that the electron energy continue to increase. And you can also measure that the electrical field as of together with electron temperature. You can understand that how electron temperature, you can see that the electrical field rises, electron temperature, we cannot measure here in the process, but you can see that the electron temperature decrease has a decay, about 20 nanosecond delay compared to that the decay of the electrical field. And the electrical field and electron temperature remain as a half EV with some kind of reflective electrical field here. So these are properties measurements of a simultaneous measurement or with the same device. It gives you a validation target for modeling. And so a similar experiment down in Ohio State tried to measure that electric field in using E-fish as a 2D nanosecond post discharge. As you can see from here, that you have a knife edge and put on top of a glass, and you form a very narrow gap. And you want to measure that if you have a if you're looking from this direction, you have a knife edge. This is only glass. You want to measure that the properties of the discharge between that knife edge to that the DBD discharge. So this is the experimental setup. This is the voltage and current, and you apply for it. The gap is about 0.6 to 1 millimeters, and so this is the experiment. You can see that is this is at the front view. You can see that this knife edge. This is at the surface of the DBD discharge of the quartz. I can see that they generate this kind of discharge with. And this is a side view. You view from this direction. You can see this is knife edge, and you see that the electric field develop and then spread on both sides of the knife edge. And this is the top view. You can see also this is probably a knife edge, and you can see that the electric field spread on the surface on both sides. So this gives you a quantitative measurement about that the electric field. And this is that the interesting result in terms of summarizing. And on the left, you measure the voltage as the electric field. What you can see that the electric field and as the voltage rise, electric field rises. But the electric field decreases as a breakdown voltage, even though the voltage continue to go up, but the electric field start to decrease. And also you can see that, and so as you can see that after that the applied voltage rise, you can still that the voltage still continue to grow. And the electric field, you can see that become a reverse and become reverse electric field, and after that the breakdown. And you can also see that if you measure electric field in x direction and the y direction, you can see that the difference between x direction and the y direction, their magnitude is different. So therefore, and this a diagnostic give you not only the time sequence about the electric field and the voltage relationship and after discharge distribution, but also give you the distribution of electric field and in 2-dimension x and y direction. They're showing that the difference and uh, in terms of the directions. Another method, old method that sometimes people ask me that why not using emission spectroscopy to measure electron number density and electron temperature? Well, people using this, for example, using argon. If you look at the argon, that this is the ground state, and there's the excited state like this, 4s is like this, and there's another like a higher excited state of 4p, and you can see. And these are the state you can using this quantum chemistry and LS coupling. You can back up that all these states can be in terminology can be populated like this. You can measure the emission lines by choosing one of the line or several lines, and try to model that the electron number density and temperature. And in this model, you need a kinetic model, very reliable kinetic model, and to do so. But if there's a mixture like hydrogen or methane into it, and you don't have a good kinetic model, and then your measurement is not accurate. Even with that, for this is experiment done by at Tsinghua University by Yiguang group. He's expert using emission spectroscopy to measure electron temperature. You can see this is a plasma discharge. This is a lens to collect that the emissions with a spectrometer and ISCCD, and to measure the spectron distribution. This is the summary of his result: electron number density measured by using argon, by using hydrogen H alpha, and in a different range, and you're showing that how that the electron number density is changing with a time. And this figure is very interesting and showing that the uncertainty in terms of electron number density distribution. This is you can see by using argon that the uncertainty quickly increase, and with the Stark, using Stark broadening, you're using a Stark broadening, that the broadening effect only accurate if the electron number density is 10 to the 17th, probably 10 to the 17th. But 10 to the 17th is very like arc, it's not applicable. But if you're using a linear ratio of multi-peaks, you can probably at some window, you can measure very narrow window, 10 to the 15th to 10 to the 14th. But if you're using the hydrogen and H alpha and H beta, you probably can measure that the electron number density to 30% uncertainty for electron number density above 10 to the 14th or 10 to the 15th. But in many non-equilibrium plasma, and this is only the region that the emission spectroscopy can measure. But in many non-equilibrium plasma, you are here between 12th, 10 to the 12th to 10 to the 15th. This is the region we are interested. So therefore, this kind of emission, even the model is accurate, it does not give you a good result of electron number density in terms of uncertainty. So therefore, still Thompson scattering and is much better way to measure electron number density, and from 10 to the 12th all the way to 10 to the 17th. And the next thing that is try to discuss is that the measurement of non-equilibrium temperature, vibrational temperature, rotation temperature, and also that the species. So here that the recent development of femtosecond laser with picosecond cores has provided great opportunity and for diagnostics. So first of all, using the broadband femtosecond laser, we are going to excite a lot of rotational vibrational levels of nitrogen and to a volatile state and form a coherent emissions. This coherent emissions form a Stokes beam, and and then you can using a probe beam to excite this after this Stokes beam and generate this kind of anti-Stokes signal, car signal. So the merit of this is advantage is that the car signal is square of the femtosecond lasers, because femtosecond lasers, the time is very short, and then you have a very high intensity. So this ultra fast pulses give you very high signal to noise ratio, and probably allow you to measure a one-dimensional distribution in terms of temperature. And also that because the Stokes beam that is automatically generated in this femtosecond laser. So you only need two beams. One beam is a pumping beam, and the other one is a probe beam. And by delaying that the time between probe beam and then the pump beam, you can to suppress that the non-resonant background noise and make you have a better and signal to noise ratio. And you can allow you to measure that the in a near surface measurement, probably to 100 and even 50 microns. So and this is that the opportunities, and at Ohio State and Walter Lampert and Igor conduct experiment using in air discharge with 100 torr, and they using picosecond laser, and they measure that the temperature as function of time. So you can see with the nanosecond plasma discharge, you can see that the air, the nitrogen in the air, you can see the more temperature rising, you have a fast heating, you have slow heating. But in the nitrogen, that you have a less temperature. Why that the oxygen in the air you have more heating is because, as I said in the previous lecture, you have an increase of oxygen, you got more the faster heating reactions going on. So therefore your temperature is higher, particularly here, faster heating is higher. And so, and also that using a picosecond laser, he was able to measure that the distribution about atomic oxygen as a function of time, and then vibrational temperature and the rotational temperature. Clearly you can see at maybe 100, within 10 nanosecond time scales, you can see that the fast heating rises the temperature of vibrational temperature and drive a little bit increase of rotational temperature. And then afterwards, there is a vibration rotational coupling, and you see that the vibrational temperature decrease and the rotational temperature increase. So this is clearly showing the mechanism as a strong vibrational excitation between vibrational levels from 0 ground state to eighth, and that's vibrational temperature rising early afterglow in this region, and due to this VV vibrational exchange populated at the high vibrational excitation. And in the decay due to the vibrational rotational relaxation, and then that the vibrational temperature is decreasing. So this figure clearly shows that the difference between the temperature. And he did that the other measurement of radicals as well. So I'm not going to repeat, because you can see the rapid heating is because there's the nitrogen reactions excited with oxygen, they generate heat, and these are also generate heat. So it created this fast heating. And another study at University of maybe Iowa by James Michael, and he using this femtopicosecond laser and to using rotation row vibrational energy to measure that the vibrational temperature between the electrode and two electrode is dBd. You can see that they measure depend on the position, and you can measure the vibrational temperature, which is here, the red one, and the rotational temperature along the function of distance. So this gives you a good understanding that the vibration temperature is several thousand degree compared to that the rotation temperature is around that several hundred degree. So it's a very strong non-equilibrium in DVD plasma. But this experiment require more complicated lasers. You need pumping femtosecond lasers. You need probe lasers. You got another probing lasers. So you need two lasers, 15-second lasers, to do this job. And at Princeton, and Tim Chen, and working with Chris Cleaver and Santia, we developed this kind of a temporal, spatially and temporally resolved femtosecond picosecond cores to measure vibrational temperatures and using rotational cores, pure rotational cores. As you can see that here, that when vibrational temperature is very high, this rotational spectrum, you can see that the tail at a short wavelength and is changed due to that the vibration temperature. By using this change, and you can using this change is because that when you have the vibrational change that your inertia, and that will change your rotational spectra. By using this kind of feeding, you can measure that a vibrational temperature. So here that the discharge geometry with this 1 millimeter discharge with nanosecond with 40% of methane, 60% of nitrogen, 60 torr, with plasma at 4 kilovolt and 500 nanosecond pulse and 20 hertz. And this is a measure that the voltage as the with plasma and without plasma and the current. Here I show you the result of measured one-dimensional distribution about the vibrational temperature, which is the red one, and the rotational temperature, the axis is here, the blue one. You can see that near the electrode, that there's strong nonlinearity of vibrational temperature and rotational temperature. And there's a energy transfer between the vibration and rotation. So this kind of measurement and give you, and is that the time sequence about that the distance, you can see this is vibrational. The vibrational energy is populate about, it's a micron, about 1,000 micron, 1 millimeter, the peak, and the peak move away from the electrode. And if you look at the vibrational rotational translation, you can see that clearly. You can see as a function of time that it is okay. And the vibrational, the temperature is increasing and decreasing in this region. There's a strong rotation of vibrational coupling near that the 800 micron, from 800 to 1,000 micron from the cathode. If you plot that dimension, you can see this is vibrational temperature. This is the rotational temperature. You can see vibrational temperature rises due to a fast heating and maintain with almost a certain area and then decrease. And during that decrease of vibrational temperature, the rotational temperature is rising, showing that the vibrational rotational energy transfer. And for a nitrogen mixture, if you have a measuring that the methane number density, you can clearly see that during this time intervals of that the high vibrational temperature, that the methane concentration is constant. That means that the vibrational nitrogen does not have enough energy to promote that oxidation of methane, and in this plasma discharge. So I probably will stop here. We'll continue tomorrow, and I'm trying to using that the rest 5 minutes to take some questions. And so tomorrow we'll continue to finish that the diagnostic methods and then plasma instability and plasma modeling. Okay, so give us some time and for tomorrow. Thank you very much, and I would like to take some questions.
So we still don't have questions, but I have a question about the rotational temperature. So when we mean for the vibrational rotational temperature is we don't sense it in the gas, right? It won't increase the gas temperature.
Yeah, I mean, vibration temperature is just representing the vibration of the nitrogen molecules.
Okay, and the rotational temperature is sensed by the gas or the translational one?
They're almost equal because the energy balance between rotation and vibration translation, you only need probably 1 or 2 collisions, you equilibrate them, and the collisional rate is so high, so they are same.
Okay. Thank you.
Any other questions?
We don't have now.
Yeah, also great. I think that the diagnostic, particularly femtosecond lasers, provide a wonderful opportunity and to measure plasma properties and non-equilibrium. And I think that there will be contribute significantly to understand that the plasma chemistry and help that developing models for modeling. All right, I'll thank you, and we'll see you tomorrow. So we talk about plasma diagnostic continually. Then we talk about the plasma instability, thermochemical instability, and talk about plasma modeling. And then we have a discussion about what is future research. Thank you very much, and have a great night.
Thank you, Professor.
Bye.